Good evening, everybody. Thanks for coming. You can hear me okay? Okay. I'm Thor Hansen. I got my degree and Ph.D. in geology and paleontology a long time ago. My specialty is clams and snails, actually. I'm not a dinosaur specialist, but I've started a dinosaur class in 1992, in fact, and after that first class, we had a field trip to see the movie. And so it has a special place in my heart, and ever since when I've been teaching the class, I show a lot of scenes from Jurassic Park, because it's just an excellent way of looking at, thinking about dinosaurs critically. In that course, I show lots of clips, not just from Jurassic Park, but also from other, documentary type films like BBC and stuff like that, showing dinosaurs. And they always show dinosaurs living, doing stuff. They have a story, there's the family, and there's the Tyrannosaur attacks them, and all this kind of stuff. And I like to show those clips because I want the students to look at them and try to be able to understand what they're seeing is based on real evidence and what is guesswork. And after a while, you can do that. But you'd be surprised at how little is based on real evidence that you see on those screens. And for instance, you might see a BBC documentary, which is a very high quality production from 1995, and they talk about everything very authoritatively. Dinosaurs did this, the Tyrannosaur did that, blah blah blah. 10 years, and it just sounds like that's what it was. 10 years later, you'll see another one by the same company, and they'll do different things. And they just say, well, this is what they did, this is what they did. And they don't talk about the evidence. They don't talk about how it's changed or how much we don't know. So that's kind of the way I want to go at this. I framed it in the ad as what did Jurassic Park get right, but that's kind of a cheap shot because we don't know what they got right. We don't know what dinosaurs were like, really. The movie had a respected paleontologist for consultant, Jack Horner. Most of the dinosaurs, the way they recreated them, were evidence-based. It was pretty good. It was mostly up to date for 1992, with some notable exceptions for dramatic effect. So they had a few things they did. I assume you've all seen the movie, mostly, pretty much. How can you not see it? And for instance, early on, there's this small dinosaur that kills Dennis Nedry, and I think that's his name, Dennis Nedry. And these big frills come up on his side and stuff. They started off with a real dinosaur there called a Dilophosaur, but the frills and the spitting is just stuck on for dramatic effect. There's no evidence for that, and they took some characteristics of spitting snakes and a frilled lizard and stuck them on a dinosaur. So they do that kind of thing every once in a while, and that's fine. But what I do want to talk about is the new evidence that's come up since then, and how we now think about dinosaurs, and you'll notice how Jurassic Park hasn't changed. It hasn't kept up with that. So first of all, what do we really know about dinosaurs? What's the evidence? And it's probably a lot less than you think. It's mainly bones. We also have footprints, coprolites. Coprolites are fossilized turds. Eggs and skin impressions. And also you might get things like the occasional things like bite marks on bones and stuff like that. But mostly it's bones. And dig the bones up. Now this is an unusually good site right here. Oh, I have a pointer right here. This is an unusually good site right here because this particular creature is actually still articulated. So it's unusual. Normally the bones just be scattered around. You might have several species mixed together. But they're all together, and so you can put together a pretty decent skeleton probably. And then you put them together. This is the Brachiosaurus, the largest, best specimen of its kind at the Humboldt Museum in Berlin. Well, now what? You're going to make a movie. Let's say you're a producer for a dinosaur movie. Make a movie about it. Well, what do you do with that? It's just this big thing. What can you tell from bones? So as an example, here are two living mammals. I'm not going to tell you what they are. They're about small dog size. You can look at the bones and we can say, well, they're small. You can look at the legs and say, well, they're not very fast, and we'll talk about how you can tell that in a minute. You can look at the teeth and go, well, they're meat eaters. And the bones tell us they're mammals. And since we have mammals still around, we know that they would have been hairy, they'd have whiskers, they'd have ears. Okay, so we can kind of make a picture. But what do you do with that? I mean, is that a movie? Is there a story there? Two small meat-eating, slow meat-eating mammals. Now, one of them is a skunk. Okay, now we have a story. I mean, they stink, they are adorable, they're nocturnal, and the other one is a raccoon. And now we have another story. And you could make a great story about a raccoon and a skunk and whatever, But there's all that stuff that you associate, all that information you associate with raccoonness and skunkness. None of that's in the bones. And so, we know that because we can see the live ones. So think of how much is missing, how much of the lives of these dinosaurs is missing to us. So here's this big dinosaur. Okay, well, it's big. It's slow. You can look at the legs and say it's a slow mover. It's a plant eater. You can look at the teeth and say it's a plant eater. It's a reptile. Has a weird long neck. What do you do with it? How do you bring that to life? What does it sound like? What does it look like? How does it walk? Does it play? I mean, what? So the fossils leave a lot of unknowns. And to really bring the animal to life, we have to find a living animal that we think is an analog for it. But the trouble with dinosaurs is there's nothing like a dinosaur today. We don't have anything at all like them. Here are three possible analogs. This is kind of a cousin of dinosaurs. It still lives. It's a reptile and it still is around. You can see what it does. This is a descendant of the dinosaurs. And this is a possible analog because it's a big plant eater with a long, weird neck. So which do we use as the analogy? Obviously the crocodile doesn't seem very appropriate. It has a totally different body and a different lifestyle. A bird for a brachiosaur? I mean, that doesn't make much sense. So typically the analog would be something like this. But it's a mammal and it's a very different kind of animal. So when they're putting together, when they're trying to recreate the life of a dinosaur on film, there's a lot of guesswork. Now, one thing they do is, remember, this is a cousin and this is a descendant. So if there are things that both of these do, then you can guess, or you can pretty much assume that the dinosaurs did them too. So what do both of these things do? Well, they both vocalize. I mean, crocodiles roar, and birds vocalize. They both care for their young. So there's certain things that they do that probably also dinosaurs did, and that's some good evidence for that. So I said there's new evidence that's come up that the new Jurassic Parks don't really take account of. And in a word, that's feathers. And let me just take a little sidestep here and talk about birds for a second and feathers. Because when you hear the word feather, you probably think of bird. So modern birds, this is a pigeon, I think. Yeah, pigeon. But almost all birds have pretty much the same basic characteristics. No teeth. They have, you see these hands here. This used to be 3 digits in its ancestors, 3 fingers, but now they're kind of fused together in something we call carpometacarpus. But it's just this weird hand structure. The feathers, the flight feathers hang off that structure and the arm. They don't have a tail. They have just kind of a short thing with this thing at the end called a pygostyle, or parson's nose, or pope's nose, we called it at the Thanksgiving table. And they have feathers. And it's the only group today that has feathers. So it's kind of, when we think of birds, we think of feathers. When we think of feathers, we think of birds. Now, here's a chicken skeleton. You can see some other weird things about it. There's the big keeled sternum. That's basically a big keel that sticks right out this way to attach the muscles for the down beat of the wing. And they have a weird back called a synsacrum, this big sort of shield-like back. The whole body is constructed to be strong but very light because they have to fly. Now, here's some feathers, flight feathers. This is the wing. These are individual flight feathers. Here's some downy material right here. And you see the feathers there's the midrib. They're asymmetrical, and they're very typical. Basically, this kind of stiff feather that looks like that indicates a flying bird. Flying feather, and here's a bit of down. Now, about the middle of the 19th century in a quarry in Bavaria, Germany, ancient lake deposits preserved some things that don't normally get preserved. Feathers don't normally preserve. But this deposit was preserving feathers and preserving various soft materials that don't usually preserve. And so this is Archaeopteryx. It's one of the most famous fossils in the world. It's about the size of a pigeon. And you can see it's obviously a bird. I mean, you look at that and you go, it's a bird. You can see the big feathers that have been well preserved. It's completely articulated. The skeleton is very good condition. It's generally considered the first bird. It has very well developed feathers. There's a picture of it. Good flight feathers. So it's doing something approaching flying. It lacks a keeled sternum, so we don't think it had a very strong beat, but whatever. Now, you notice here's the pigeon, here's a typical dinosaur, and here's Archaeopteryx. And Archaeopteryx has teeth, has a long bony tail like a dinosaur. It has arms and fingers like a dinosaur. It has a normal hip. It's basically a dinosaur with feathers. But because it has feathers, we call it the first bird. Doesn't have any of this other stuff that I talked about. So and in fact, specimens of this had been found prior to the famous one with feathers, and they were just classified as a dinosaur. When they found the feathers, oh, it's Archaeopteryx, it's the first bird. So this is what we call a cladogram, excuse me, and it's not exact. It's kind of it's sort of like an evolutionary tree, but it's basically what it is. It's a diagram that shows relationships, and this is a tree for the Theropoda, which is a group of dinosaurs that basically include all the two-legged or bipedal carnivorous dinosaurs. There are a few in here that aren't carnivorous, like Therizinosaurs, but it's the Spinosaurus, the Allosaurs, Tyrannosaurs, all those kinds of things, the Raptors, they're all in that group, the theropods. The birds are descendants of that. And here's where they sort of have stuck Archaeopteryx near Dromaeosaurs. Now, Dromaeosaurs is the scientific name for the raptors, or Velociraptor and Deinonychus and things like that. So they're close related. And it has been assumed for a long time that, well, we have all these dinosaurs, and then this one right here developed feathers, and they became birds. Okay, good enough. Until, now I guess in the late 90s, I guess it was, or early 2000s, I can't remember the date. In China, they started finding, they had some new localities they started looking at that had lake deposits that had preserved feathers routinely. And they started finding a lot of dinosaurs with something on them, feathers or some kind of coating like this, what they're calling proto-feathers, like a down. And let me just check, I want to make sure that okay, just got to keep an eye on my time here, because I'm used to 50-minute time, I'm a lecturer, I just would go on if I had to, if I could. So there's the fossil, there's sort of a close-up of it, and there's a reconstruction of it. It's a furry little guy. Well, it's not fur, it's like downy, okay? And in the last couple of decades, they've been finding feathers all over the place. True feathers, meaning veined big feathers down to here, on these things called Therizinosaurs, oviraptors, Dromaeosaurs. Proto-feathers all the way down to here. Now this includes Tyrannosaurs, fuzzy Tyrannosaurs. And then recently they found some proto-feathers all the way down to here. So it looks like almost the whole theropod group had some kind of coating on the outside, some sort of feathery coating. Now, it also means they're probably warm-blooded, because you can't be cold-blooded and have an insulative coat. So here's a small tyrannosauroid, in the family Tyrannosaurs from China, feathered, or furry and fuzzy. I'll just say fuzzy. I don't want to say furry. Here's a Tyrannosaur, Tyrannosaur Rex parent, and here's the chick, kind of a fuzzy chick. Feathered Eutyrannus. So these are sort of medium-sized tyrannosaurs. And here's, I'm not sure what these are. Remember the scene in Jurassic Park with Gallimimus running across the field? This is the scene, and this is what it looked like in 1992. This is what we think it looks like now, or this is our current view of it. This is interesting. I mean, this is one thing to have this kind of feathery coat, but then these big feathers on the arms. What? Why? We don't know. Now, I want to drill down a little bit deeper into Dromaeosaurs. I could say something about almost all the dinosaurs in Jurassic Park, make comments about it, but we don't have time for that. So I want to just talk about spend a little time talking about the villains in the movie. They're the villains, and they're the main characters, really. So this is what they call Velociraptor in the movie. This is from one of the more recent ones with Chris Pratt. And Velociraptor is a name. Oh, by the way, this is a newer look for it. And here are a couple of other looks for it. We don't know. These are guesswork, but based on other relatives, they would, had a feathery tail, large feathers on the wings, etc. So this is a picture of the skeleton. Now, this is a very busy slide, but I'll just point out a couple of things here. This is the skeleton of a dinosaur called Deinonychus. This is what they're calling Velociraptor in Jurassic Park. It's actually a North American species called Deinonychus, or genus called Deinonychus. This is what the actual Velociraptor looked like. So both of them are raptors or Dromaeosaurs. They're characterized by these big sickle-shaped claw on the hind leg. This would be the Asian version. This is the North American version. So for some reason, they used Deinonychus in the movie, but they called it Velociraptor, maybe because the name just sounded cooler. Here's the foot. Had two claws it would run on, or two toes it would run on, and then this retractable kind of slashing claw. When it was found in 1964, it was quite astonishing, because at that time, everybody thought that dinosaurs were slow-moving, cold-blooded, the typical kind of lizardy kind of things. And then they find this dinosaur that that looks pretty fast and has a weapon and it's bipedal, has the weapon on the hind leg, which, all of a sudden, this sounds very ninja-like, getting up and slashing with the hind leg like a fighting cock. That doesn't sound like a slow-moving sort of a cold-blooded reptile kind of thing. This is a specimen of it. Now, Deinonychus is just a little fellow. It's only about this tall. This is a specimen in the Yale Museum, Peabody Museum at Yale. And it's just a spindly little thing. And it wasn't big enough to be scary for Jurassic Park, so over the objections of the paleontologist, Spielberg made it bigger. And as it happens, while the movie was in post-production, they found a new type of raptor called Utah raptor, and this is the sickle claw of Deinonychus. This is the claw of Utah raptor, and so they found a raptor that was as big as the one in the movie. So that was kind of fortunate, I suppose. Not that anybody really cared, but now let me just check. Oh, sorry. Okay. Now, let's drill down a little deeper and use some evidence and try to answer some other questions. How fast, how smart did they hunt in packs? Now, there's a scene in the movie where, what's the guy's name in the movie? The paleontologist's name? Grant, Dr. Grant, asks Muldoon, the game warden there, about the raptors. And he says, what are they like, And Muldoon says they have cheetah speeds. They're very fast. They have cheetah speeds. They're very smart. They act in groups, and they remember things, and they figure things out. And they act in groups. They're very smart, and they have cheetah speed, so they're very fast. So let's do a little research on that. This is what I do in my class. This is the human skeleton, and let's look at the leg. And you have several bones in the leg that you should be familiar with. The thigh bone is the femur. The shin bone is the tibia. And there's a little bone behind it called the fibula. And then in your foot, there's something called metatarsals. That's kind of the long bone in your foot. Okay, so what's this? Femur. What's this one? Tibia. And in your foot is metatarsals. Good. So once you know that, you know the bones for every four-legged animal on the planet, because they're all the same. We all basically evolved from amphibians. So this is an armadillo, this is a coyote, this is antelope. So it's the hind legs of three different animals arranged according to speed. Slowest, faster, fastest. Now, here's the femur, tibia, fibula, tibia and fibula, tibia, fibula. Metatarsals, metatarsals, metatarsals. What do you see as a difference? What happens, how the legs differ in a fast animal versus a slow animal? What?
Bigger tibia, bigger metatarsals.
Okay, longer tibia and longer metatarsals, especially the metatarsals get really long. Here the animal is walking on its foot, basically. Here, the metatarsals become part of the leg segment. And here, they're even a longer part of the leg segment, and they're reduced. There's just one long bone versus 4 bones here and 5 bones here. Also notice that they start to run. This is walking on its foot. This is walking on its toes, because the metatarsals are here. This is walking in the tip of its toes. Okay, so they get more upright. They call this ungular grade stance, and this is digitigrade stance. Okay. You also notice that the fibula gets smaller and it becomes less important. All right. So here's 4 different skeletons. Which is the fastest? A. Which is the slowest? D. Good. Which is between B, now this is an antelope, this is an elephant. Between B and C, and just look at the hind legs, which looks like the fastest?
C.
Good, C. See long metatarsals here, shorter metatarsals here. You guys are paleontologists. So here's a race. Here's a cheetah. Here's a gazelle, dog, horse, elephant back here. Okay, so we got that figured out right. Here's the 2 bipeds are humans and the ostrich. The ostrich is pretty fast, but it's back a ways because it's a biped, and no biped the fastest biped is not as fast as the fastest quadruped or 4-legged animal. So it can't reach cheetah speeds. That ostrich can't. Now, here's the Nauticus, and here's an ostrich. Look at that ostrich leg. Look at that short femur. Look at that tibia. Look at those metatarsals. Oh my God, they're like as long as the tibia is. Here's the Deinonychus, short femur. Here's the tibia. Here's the metatarsal, kind of short. Does this look as fast as an ostrich? No. So it's not as fast as an ostrich. So cheetah speed doesn't make sense for that. Okay. So that's not good evidence-based. Do they work in packs? There's actual evidence for that. So there's a couple of sites where there's this dinosaur called a Tyrannosaur, which seems to be a favored prey for Deinonychus or these raptors, where they're associated with the remains of multiple Deinonychus, like lots of Deinonychus teeth and stuff that were feeding on it. When dinosaurs fed, when carnivorous dinosaurs ate things, they lose teeth routinely and just grow new ones, like sharks. And here's another site where it looked like there was a group of raptors attacking this Tyrannosaur. So it does look like they worked in groups, and they were small, and this was a much bigger animal. So lots of times I'll see reconstructions of them in their hunting mode, sort of like wolves, like a wolf pack harrying the prey, although they had different weapons than a wolf does. How smart were they? Now, the encephalization quotient is a figure that refers to the volume of the brain relative to the body size of an animal of that type, expected for that type. It's kind of it's a bit of a fudge factor in there. It works pretty well in determining intelligence for sort of medium-sized animals. In other words, animals about human size, pig size. It starts to get wrong when you get to really big animals or really small animals. So you can see here, humans are at the top as the biggest encephalization quotient. An elephant is very smart, but it's down here because it's very big. But in this range, it's pretty good. And notice that humans are here. Here's dolphins and monkeys and chimpanzee. Dromaeosaurs and troodontids are way up here, right just next to humans and above the primates. Whoa. So there's evidence that they could have been really smart. And what's really cool is they had hands. And things like birds, like not all birds, but parrots and ravens and stuff are very smart, and they use tools. So I love the idea of a raptor picking up a stick or something and doing something with it, you know. But we have no evidence for that, but I think it's a great notion. Now, the thing I want to leave you with here is something called Troodon, which is closely related to Dromaeosaurus. You see it has a little sickle claw here. It's a little bit more lightly built. And here's an old reconstruction of Troodon. Oh, there it is, you know, kind of a typical dinosaurian look, scaly skin and whatever. Recently, they found a relative of this animal, very well preserved, not only with feather impressions, but with chemical signatures in the feathers that told us what color they were. So this fossil allows us to literally paint a picture of a dinosaur, just like if Audubon went back in a time machine and painted a picture of a dinosaur. And this is what it looked like. Anchiornis. And you look at that and you go, that's a bird. With a long bony tail, has teeth, big feathery wings, and feathers on the legs. What's with the feathers on the legs? Well, that's having a flight surface on the legs is typical of gliders. And so here's another image of one up in a tree, about to jump out. In this case, it's going to grab this dragonfly or something like that. But this is very closely related to the Dromaeosaurs. Big feathers on the wings and feathers on the legs. I like the idea of moving away from the raptors, you know, running around in packs on the ground and looking lizardy or kind of looking reptilian, and hanging out in trees and just basically skulking in trees and waiting for something to come by and swooping down on them or jumping down on them. Anyway, that's all I wanted to say. I think we have a few minutes left if you have any questions. Do you have any questions?